Welcome to the Explainer. Today, we're going to break down the architecture of Cisco's software-defined access. We are going to deconstruct the fabric piece by piece, so you can really understand the specific roles of all the network nodes that make this thing work. So here's our game plan. We're going to start with the high-level blueprint, the 30,000-foot view. Then we'll dive deep into the control plane, the border nodes that act as gateways to the outside world, and of course, the edge nodes where all your users connect. And to wrap it all up, we'll look at some of the key design choices you'll face when you actually go to deploy a fabric. Okay, first things first. To really get a handle on SD access, we have to look at the entire ecosystem at once. You need to see how all the pieces fit together before we start taking them apart. And here it is. This is the complete blueprint of an SD Access Fabric site. You can see that management layer up top with DNA Center and ISE, and right below that, the fabric itself with its really distinct nodes. You got your border, your control plane, and your edge. To really get how this all works, let's break down the specific job of each of these key players. Think of these as the core building blocks of the whole system. Up top, you've got the brains of the operation, DNA Center running the automation, and ISE handling all the identity and security policy. Then, inside the fabric, you have the control plane nodes acting as a directory, border nodes are your gateways, edge nodes are the on-ramps, and the wireless controller brings all your wireless users into the fold. Each one has a totally distinct and absolutely vital job to do. All right, let's really focus in on that command center, the components that manage and control the entire fabric. This is where all the intelligence of the system really lives. So, the control plane node, what is it? Honestly, the best way to think about it is as the fabric's own personal GPS. It runs this mapping system using the LIST protocol, and its whole job is to keep track of every single endpoint. It knows who every device is and exactly where it's connected to the network at all times.
So what that really means is this node is basically a central directory, kind of like a phone book for the network. It keeps this simple database that maps an endpoint's identity, that's its IP or MAC address, to its current physical location. So, whenever an edge node needs to send traffic to another device, it just asks the control plane node, hey, where's this endpoint? And bam, it gets an immediate answer.
Okay, we've seen the brains. Now let's move out to the perimeter of our fabric and see how it actually talks to everything else. And that is the job of the border nodes. If the control plane is the GPS, then you should think of the border nodes as the shipping and receiving docks for your fabric. Any traffic that has to leave the fabric, whether it's going to the data center, another campus, or out to the internet, it absolutely must pass through a border node. And, you guessed it, any traffic coming in has to enter here as well.
Now what's really interesting is that border nodes are not all the same. This table breaks down the different roles they can have. You've got your internal borders, and those are for connecting to trusted parts of your own company, like a data center. Then you have external borders for connecting to the great unknown, the internet. And finally, you've got an anywhere border, which is kind of like a Swiss Army knife that can do both jobs at once. The type you pick really just depends on what network your fabric needs to talk to.
And this visual just makes the difference crystal clear. Look on the left, the internal border is connecting to your known networks, your corporate data center, your shared services. But on the right, the external border connects to unknown networks, and that's your path out to the wild west of the internet. Okay, so the key thing to remember about an internal border is that it's a two-way street for routing information. It tells the rest of your company how to reach the networks inside the fabric, but it also learns routes from those trusted networks and brings them into the fabric. This is exactly how your fabric users can reach all those internal servers and services. Now, in contrast, the external border is a much more secure one-way exit ramp. It'll advertise the fabric's addresses out so return traffic from the internet can find its way back, but, and this is absolutely critical, it does not import any external routes into the fabric. It simply provides a default path out. That's it. All right, let's get to where the real action happens, the edge nodes. These are the on-ramps for all of your wired users and devices, connecting them directly into the intelligence of the fabric. In a traditional network, you just call this an access switch and be done with it. But in SD access, oh man, the edge node is so much more than that. This is where your computer, your IP phone, or your access point physically plugs in and actually becomes a part of the fabric. So this process really shows you all the intelligence that's packed into the edge. The second a device connects, the edge node sees it and registers it with the control plane. Then it places it in the correct virtual network for segmentation, gives it a consistent gateway, and then for any traffic it sends, the edge node queries the control plane to find the destination and wraps the packet in a VXLAN header to tunnel it across the fabric. It's a whole lot more than just a dumb port.
And this slide right here, this illustrates the absolute secret sauce of Lisp that makes the whole fabric work. It's all about separating identity from location. The EID, the endpoint identifier, is the device's IP address. That's who the device is. The RLOC, the routing locator, is the IP address of the edge switch it's connected to, and that's where the device is. By completely decoupling who from where, the network gives you that seamless mobility.
Okay, for our final piece, let's look at how you can actually combine or separate these roles depending on what your network's design goals are. This is all about how you physically build out your fabric in the real world.
So here you can see the two main design patterns. On the left, we've got what's called a collocated design. That's where a single, beefy device does both the border B and the control plane C functions. Then on the right, you see a distributed design, where those roles are split up and run on separate, dedicated devices.
So which one do you pick? Well, it really just comes down to that classic trade-off, simplicity versus scalability. The co-located model is way simpler, which makes it perfect for smaller sites. The distributed model, on the other hand, is much more scalable for those really large deployments, but it does come with a bit more configuration complexity, like needing BGP to keep all the separate nodes in sync.
You know, this quote here really just sums it all up perfectly. SD Access isn't just one thing. It's a completely integrated system that brings together the automation from DNA Center, the security policy from ISC, and all the advanced networking capabilities of the fabric nodes to create one unified, intent-based network.
And that leaves us with one final design question to chew on. Now that we understand all the individual roles, the brains, the gateways, the on-ramps, the real art begins. How do you strategically combine all these components to build a truly resilient network, one with no single point of failure? That right there is where the real planning begins.